Okay, hello and welcome everybody. This is the first chapter of actual meat that we're getting into for PDEs done right. I'm calling this chapter preliminaries. We're just going to cover section 1.1 today. It's going to be a bit of a long section, maybe one of the deeper sections of the entire course, which is a little bit unfortunate that we're jumping right in. But it's deeper conceptually. We're not getting into a lot of math, we're getting into a lot of thinking, okay? So we're going to start out by trying to define a partial differential equation. And to do that, we actually have to start with equations, right? Because I think a lot of people don't think that hard about what an equation actually is. An equation is a mathematical equality containing at least one unknown variable. Any sort of equality that we construct where there's at least one term in the equality that's not yet known. And this equation doesn't necessarily have a truth value by itself, since the variables is or are undefined. But once we define the unknown, then we gain a truth value. It's either going to be true or false upon making that definition. And that's, in fact, we're going to see what a solution is. But let's look at an example first. First example is going to be an equation of light. And I know since I have inverted the colors on these videos, the colors don't show up nearly as nice as they do in the book. But in the book, this is actually red, this is actually green, and that's blue, the colors of the words. And we can construct an equation. We could say the equation of light is red plus unknown equals magenta, and we just don't know what the second piece of light is to add into our equation to gain magenta. But that leads us to the solution, right? The solution of an equation is a definition of the unknown variable under which the equation gains the value true. Okay, so in this case of light, we're going to define, now this is the colon equal sign, and I'm going to try to stick with this in the book, is the one version of saying defines, right? It's an equality, but it's a definitional equality. It's a way to say unknown is actually equal to blue. And once we make that definition, then red plus unknown equals magenta becomes red plus blue equals magenta. And when it comes to light, red plus blue does in fact equal magenta. This is a true statement, and so we have solved the equation. So common occurrence is when multiple equations are related to one another through multiple unknowns. This is the domain of systems, right? Systems of equations, which you probably encountered all the way back in Algebra 2, maybe even Algebra 1, I don't remember. So a system of equations is a collection of more than one equation, more than one unknown. We can do this with light if we want. We can say red plus unknown 1 is unknown 2. Unknown 1 plus unknown 2 equals yellow. And the yellow really doesn't show up well for me. I have no idea how well it will when I invert things. But this is a system of two equations with two unknowns. So ideally it has a solution. I don't actually present the solution here. I think in one of your exercises I do though, or I ask you to. Now it's important to note that we weren't defining these equations numerically, right? I think the point that I had when I came up with these examples was that equations don't have to have numerical values on either side. They're useful when they do, but they don't have to. But once they do have numerical values, we call them numerical equations. So numerical equation is any equation whose values are elements of number systems. Here's a great collection of number systems. We've got the naturals, the integers, the rationals, the reals, the complex numbers. These are known as, you can either call them the prime fields, you could call them Z mod P. We have the right half number line. We have here the Gaussian integers, the p-adics. There are just so many great number systems out there that can all be explored, and you can create numerical equations with them. A classic example of a numerical equation is finding the roots of a cubic polynomial. So here's a nice example. There's a cubic polynomial for us. 3x cubed minus x squared plus 11x minus 4 equals 0, right? It's polynomial before it equals 0. This is a polynomial independently on the left. But the fact that we set it equal to 0, it's an equality now. We have an equation. And this is a numerical equation. So we'll note that the equation itself has been paired with the statement of the domain, actually. This statement, x is in R, is telling us where are we actually looking for the unknown, right? What is the domain that we're searching for the unknown in? And with a numerical equation, this had better always be some sort of number system. The mathematicians adore abstraction. We like to say, hey, rather than thinking about numbers, let's think about maps which take one number to another number and form equations out of those. Now, these maps are called functions. You've been working with them for a very long time. The equations which take the values of functions are called functional equations. So a functional equation is an equation whose values, right? So it's not going to have numbers on the left, numbers on the right. It's going to have functions on the left, functions on the right. And so those values are elements of function spaces. I have this remark in here to say, okay, just like numerical equations care about domains, function equations care about domains. Okay, so we're always going to pair a functional equation with its domain. Like this is the space of functions we're trying to find an answer within. So let's look at some of these spaces of functions. We're going to start with kind of just 4 that are kind of all related to each other to get us rolling. And this first one's called the continuous functions over an interval. So if we have some interval in R, call it x0 to x1, that's an interval, we define capital C of this interval as a space. Okay, so there's my definitional equality. It's defined as a space, or it's defined as a set. These curly brackets are telling me that this is a set. It's a collection of things. What's it a collection of? It's a collection of functions. Now this is function notation. For functions, it does what? The function takes this domain, the interval, and outputs R. That's what this means. And then when I have my curly brackets, I'm going to say this is the objects in the set, but the objects all satisfy a certain property. So maybe I'll make that clear. So this is a set. This is a collection of objects in the set. It's a collection of objects in set. This, on the other side of my vertical line there, this is a collection of properties the objects satisfy. So if you've never seen set notation, this is what's going on with set notation. We have a set denoted by the curly bracket. It's got a collection of objects on the left and a collection of properties that the objects satisfy on the right. So let's talk about what these properties are. These properties are the limit as x goes to x star. So x star is, I'm trying to say there's a special x there. So when x goes somewhere special, the function equals where it is when it's special. So this says the limit of the function is equal to the value of the function, which is the definition of continuity. And that's why we have ourselves the collection of the continuous functions over the interval 0, 1, x0, x1. We can extend this definition. We can give C some powers. Okay, this is a common way of denoting smoothness. So we say these are the n times continuously differentiable functions over this same interval. So we give a superscript n next to C, and now we say, hey, actually, remember this is my collection of properties. So I have functions here, now they have properties. The properties are that the derivative, the nth derivative, exists, and the nth derivative satisfies this definition of continuity. So that's why we call these the n times continuously differentiable functions over the interval. We like to be cool with our notation and add an infinity in the power instead on C and say these are actually the smooth functions or the infinitely differentiable functions. And here I'm saying here's my collection of functions. They all have a specific property. What's the property? Well, it's that the derivative exists for all natural numbers. And that would be infinitely many derivatives. Finally, a really common set of functions that we'll see is useful for the Fourier space when we talk about Fourier series and Fourier transforms is L2. L stands for Lebesgue, by the way. It's a Lebesgue space. Fancy French guy. Doesn't look like Lebesgue when you spell it, but it's written like this. So it's a Lebesgue space, but we often just call this L2. This is the space of square integrable functions over an interval. What do I mean by square integrable? Well, what I mean is here's my functions. It's my set, right, of functions. What property do they have over their interval? The property is that the integral from x0 to x1 of that function squared is finite. Okay, so we use this notation less than infinity in mathematics to denote that the integral exists, and in fact it's finite. Okay, so if I'm strictly less than infinity, that's what I mean when I say finite. So this is a common space. We're going to see it when we encounter the Fourier series and the Fourier transform. So keep this one in mind. The different continuously differentiable spaces are common for us because we are going to be working with differentiable functions because we're solving differential equations. So that's why I've introduced the sets of functions that I did. Let's look at some examples of functional equations. One example is the integral equation. So this is an example of a functional equation. This is 0 on the right-hand side. Truly, it does have a numerical value on it, and that's only because the integral takes the function on the left and outputs a 0. But the important part about it being a functional equation is that my unknown, right? My unknown has the value of a function. So I'm looking for unknowns f in the continuous functions on the interval -1 to 1, and I'm looking for the ones of those whose integral is equal to 0. This is an example of a functional equation. And in fact, once again, I've given myself the pairing with the domain. F is in the continuous functions. There's this another example. I'm calling it the exponential equation. You may not find out why until you do one of your exercises at the end of the chapter. But this is a nice functional equation where both sides do in fact take the value of functions. We're saying, hey, a function of x plus y on the inside of a function is equal to that function on x times that function on y independently. Okay, so this is now a question of what sort of a function has this property. It's going to be, and we're looking for this function in C infinity, so that means infinitely differentiable functions on the entire real line, right? And I guess I could have probably notated this as C infinity of R as well, either one. Now, a differential equation is going to be a special type of a functional equation, right? It's a functional equation which involves at least one derivative. So let's look at our definition here. So differential equation is a functional equation where at least one derivative of the unknown is computed. So I have a functional equation. Imagine there's a derivative on there. That's a differential equation. If I jump up here, all I have to do is put a little prime there, or in this case, since it's a function of two variables, maybe I put partial x here, and now either of these are differential equations, just because a derivative has shown up. So as long as a derivative shows up, they're differential equations. In this case, there are no derivatives, so neither of these are differential equations. But this gives us an idea of what we're looking for when we're trying to identify differential equations. An ordinary differential equation is going to be any differential equation in which the domain of the functions involved is one-dimensional. Okay, so when we're talking about ordinary, we're talking about the domain of the functions involved. Not the collection of functions we're solving over, their domains, right? So what are the inputs to every function we're solving for? If that input is one-dimensional, then we're talking about an ODE. If the input is anything more than one-dimensional, right? With a PDE, a differential equation in which the domain of the functions involved is d-dimensional for d greater than or equal to 2. So if I'm looking at whatever function I'm solving for, and I have reason to believe that that function depends on more than one dimension, then I have a partial differential equation. And that's the only difference between the two. It doesn't care about the values the function takes. It cares about the inputs to the function. The order of a differential equation, you probably experienced this in your previous course, is going to be the largest power of derivatives which appears in the equation. So if we just jump back up to here, imagine that I go ahead and I add not 1, not 2, but 3 primes to f inside of this integral equation. All of a sudden, that's a third order differential equation. Now, it's also an integral equation. It's technically called an integro differential equation in that case, but it's certainly a differential equation. If I would have put partial x on the left, and suppose I put partial y squared on the right, then that's a second order differential equation. And we see that in my examples below. In my examples below, we've got a functional equation here. Y double prime minus the square root of y prime squared plus 1 equals cosine of x. I'm looking for y's that are continuous and twice differentiable in the interval 0, 1. This is going to be a second order ordinary differential equation. It's second order because there's one derivative, but there's two. It's ordinary because there's an independent variable, and I'm just going to make the assumption that y depends on this independent variable x. Okay, so y is a function of x. Its input is one-dimensional. Therefore, it's an ordinary differential equation. The functional equation I have here, partial t of phi equals phi squared plus 2 phi partial of x of phi. Notice I've got t as a independent variable, and I've also got x as an independent variable. All of a sudden, my phi must depend on both t and x. That's 2 dimensions, and so I have a 2-dimensional input to phi, which means that phi, this differential equation is a partial differential equation. Now, I'm calling it second order here, and I think that's actually a mistake. This is a first order partial differential equation, because if we look at the total power of derivatives here, the total power of derivatives is only 1. So let's talk about why we study partial differential equations. We should note that all equations really just represent relationships, right? We're trying to say how many or what behavior of some object equals how many of a different object or different behavior of a different object. We're comparing things. But they're compared very closely in a perfect relationship with the equal sign. And so with a partial differential equation, what we're comparing is a change, right? We're comparing a change perhaps in time with a change in space. And physics, the natural interpretation of reality is that not only do things vary in time, but they also vary in space, right? I could, stand in the middle of a road and see cars pass. They're going to be changing. Whether or not there's a car in front of me is going to change over time. Whether or not the car, exists in one spot in space is going to be a yes/no thing. So there's going to be derivatives in both time and space. And so if I want to represent anything that moves in both time and space, or differs in space and moves in time, then I have to use a PDE. So that's why we care about PDEs. We're going to look at some examples of what is often called the holy trinity of PDEs. And these are second order linear PDEs. And we'll look at all of these. So the first one is the shape of a bubble. Okay? So we're going to imagine that we have a wire that I stretch in space, and I realize it's not very easy for me to draw a wire in 3D on a 2-dimensional screen. But suppose I've got a wire in space, and suppose I dip it in a soap solution and I pull it out, and I get some soap film that stretches between the sides of the wire to make some sort of a bubble. So imagine that's my soap film in between the wire. What shape does that take? How can I tell what shape it's going to take before I pull it out of the water? And it turns out that PDEs can give us this answer. The way PDEs give us this answer is a bit interesting. We're going to say, okay, the average height of the wire is going to be 0. However the wire is oriented, we're going to call that 0. And we're going to give the height of the soap film the name phi. Since the height of the soap film varies on the left-right position, as well as the forward-backward position, we have to assign 2 spatial variables. So let's go back. I'm going to put my wire. This is my 0 for height. Imagine my wire evolves around this 0 for height, and the soap film comes through like this. Then we have the soap film can change in the left-right direction, and it can change in the forward-backward direction, and then it also changes its height, but the height we've given the name phi. Okay, so phi now, height cares about the left-right direction, it cares about the up or the forward-backward direction. Phi is a function of x and y. So then we ask the question about changes, right? We ask the question, does a change in the x direction, does this slope right here affect the change in the y direction, the slope in the forward backwards? If the answer to that is yes, then we have a PDE. Now, it turns out that you have to be a physicist very briefly. So you think about surface tension. So at any point on the soap film, surface tension is trying to pull it flat, right? If there's a tension to any point in all directions, and if you think about it, if you have a piece of cloth and you pull on it from all directions, it pulls the cloth tight and flat. And so what happens with surface tension is it's trying to pull it flat at any point. And the idea is that a way to talk about flatness is to minimize the curvature in absolute value. Okay, so you get a positive curvature, you get a negative curvature, but flat curvature is 0. So we're going to minimize that in absolute value, or gain curvature of 0. And you can actually compute curvature of any surface by the equation that I have here. It looks pretty bad. Doesn't look like something we want to work with. But all we say is that, okay, fine, let's imagine that number is pretty small, that number is pretty small, that one's small, and that one's small. Now you're thinking like a physicist, and what this does is it reduces to second-order partial derivatives in both the x and the y direction. And we're saying we want this curvature to be as close to 0 as possible, so let's let it be equal to 0, except for maybe at the boundary. And so we let the curvature be 0, and now we all of a sudden have an equation, right, because this is an equal sign to 0. So we have some phi, we need its x direction derivative, second derivative, and its y direction, second derivative, to add to be 0. So there's a PDE, but the shape of the wire didn't play a role in this PDE. And that's something very interesting, right? So the question is, we derived a PDE, but it said that, it's just talking about curvature, it's not talking about the shape of the wire itself. Where does the shape of the wire come into play? And this is something very special about PDEs, is that they really care about boundaries. Okay, so back in ODEs, you probably had some boundary value problems that you worked with. But boundaries are trivial in one dimension because the boundary of any interval is just 2 points. It's the endpoints of the interval. In 2 dimensions, the boundary of any shape can be a lot of things, right? It can be a circle, it can be a square, it can be a triangle, it can be anything much more complicated than any of those. It could be a starfish, which I guess is a star. But it can be anything in 2 dimensions, even worse in higher dimensions. So we really care about boundaries in PDEs that we didn't care about in ODEs. And this is where the shape of the wire comes in. So we have to talk about the boundary conditions. The way we make the boundary conditions meaningful is we just assign the height of the wire a name. We call it f. This is one of those examples of what I was saying from the foreword, if you watched that video, where I use f to describe something that we know, but we're just going to keep it general, where phi is going to be the thing that we're actually trying to solve for. So we know f, it's the height of the wire around the boundary. And so what we say is that the PDE becomes this boundary value PDE, where we have the actual partial differential equation on one line, and we actually assign a boundary value on the other line. We say, hey, this soap film has to be equal to the function that describes the wire. So on the wire, the soap film is equal to the wire. Not really a surprise, but just something that we want to keep in mind. Make sure that shows up as a wire. So on the wire, the soap film is equal to the wire. And that's just something you have to add, and you have to condition on that when you're solving the PDE. So there's actually a lot of functions that solve the top case, but there's only one function that solves the top case and the bottom case that passes through that exact height that the wire is describing. And that's where we would come up with the shape of the soap film. Another example is with the propagation of heat. So if we have a lump of metal, and we're going to heat that metal to a specific temperature, maybe to make it pliable, we call this my lump of metal. We're going to heat it, put a little flame on one side. So we're going to heat it from one side, and it's going to get a little hot here. Okay, so let's give it some red hot on the one side. We're going to heat it. And then we're going to take the flame away, and we're going to ask ourselves the question, okay, how does the heat propagate through the metal? It's an important question, because if we only have the ability to heat the metal from one spot, we really want it to spread if we're trying to make the entire piece pliable. So how long would it take for this heat to spread and equilibrate to the whole piece of metal? So that's a question we can ask, and we can in fact answer it with PDEs. So we're going to give the temperature of the metal a name, phi, and this is going to be the temperature at point X, Y, Z. Right, so at the point X, Y, and Z, that's going to be the temperature of the metal. But in fact, that temperature is going to change over time. And so it's also going to be a function of time. So in fact, phi here is a function of time, X, Y, and Z. It's a function of 4 variables. And if we're talking about PDEs, we have to ask the natural question, does the temperature over space, which we can represent with the gradient, right? I will call the gradient nabla. It's the name of the symbol here is nabla. I know it's a really annoying name, nabla. So I'll call that nabla phi, or gradient of phi. So how does that, the change over space, affect the temperature change over time? And we have to, once again, think like a physicist here and say, well, Newton's law of cooling says that the heat flow is proportional to the difference in temperature. This is, over an infinitesimal amount of area. But what this is saying is we can give the heat flow a name Q that's going to be proportional, so there's some constant here, to the difference in temperature. Now the difference in temperature is the gradient, right? Gradient is calculating change over space, so the change of temperature over space is the gradient, and the heat flow is proportional to that, so it's got a negative K out front. Now it's a negative K because we're going to lose heat, right? We always lose heat if it flows out of an area, if I have a gradient. But that's going to be the heat flow. And the K here is actually going to describe the thermal conductivity. You don't have to worry about that for now. We're just trying to derive an equation. And how could we relate heat flow back to an overall temperature? Well, if we think locally, the temperature change over time is either going to be positive if the heat's going to be flowing towards a point, or it's going to be negative if the heat's flowing away from a point. Right? And we have a way of describing the overall vector field. The gradient is going to be a vector field. That's why I gave my Q a boldface. If you watched my foreword, I talked about boldfacing vectors. So Q's boldface, Q's a vector, it's a vector field. And we have a calculation which describes vector field behavior toward or away from a point. It's called divergence, right? And it's represented by nabla dot, right? There's a dot right there. So you compute the dot product. And a positive divergence represents away from, so what we need to do is include yet another negative sign in our PDE. So we can calculate that the change in the temperature is going to be some proportionality constant times negative times the divergence of this heat flow. And if we compute all of that all the way out, what we get is that the change in temperature over time is now a positive quantity. And then you have nabla C dot nabla, or nabla dot product itself, the gradient dot product itself. That's going to give us the squares of the derivatives in each of the directions. This is called the Laplacian, and we represent it with delta. But we end up saying that the change in time of the temperature is equal to, or it's proportional to the square, the second derivative in space on phi. And so this is going to be our heat equation, PDE. That should be positive, not negative on alpha. So that's the heat equation, PDE, and it describes the flow of heat through an object. But we do have to talk about boundary conditions again, right? Because our metal exists somewhere. We've got metal here, and it was hot on one side, but it exists in the air, right? So we've got air out here that the metal exists within. And so there's a boundary between the metal and the air, and we have to describe that boundary. Well, let's just say the air has a temperature of 300 Kelvin. So we'll say, hey, the temperature of our metal should be 300. Well, really outside the metal, right? Everything outside the metal should be 300. There's our boundary condition. But that's a boundary condition in space. And you'll notice we care about time as well. So what is the boundary of time? One way of thinking about the boundary of time is that the boundary of time is the present. Right? If we're calculating something about the future, the farthest back time can go is the present. Like the edge of the future is the present in some way. And so we need a value for the temperature at the present or at the beginning. But we know that. We know a value of the temperature at the beginning because we have our hunk of metal and we knew what its original temperature was and we knew exactly where we were heating it for how long, so we know its temperature at that point as well. So we know the value of the temperature at the beginning, we just don't know the value of temperature in the future, and that's where we're going to have to solve that equation subject to some boundary conditions. Okay, and finally, in the holy trinity of PDEs, we have the height of a wave. So a very classical example is where we drop a pebble into a pond, and everything ripples out from where we drop it. And so we're going to try to measure the height of the pond at any given point in time. Well, the pond has some left-right directions and forward-backward directions, and so certainly the height of the pond depends on x and y, but of course the height of the pond varies over time, otherwise the ripples wouldn't travel anywhere. And so we have partial derivatives in x and y, we have a partial derivative in time. We're going to ask ourselves the question, how do the variances in space affect the variance in time? And it doesn't take too much intuition to figure out that certainly they should, because if I have a really steep wave, it should spread out really quickly with our intuition. I'm not going to get into the derivation here, we will eventually in this book, but the way that we can relate them together is actually with second derivatives. So we have two derivatives in space added together. This is once again the Laplacian. On the right is actually two derivatives in time now for the wave equation. There's a wave speed of c. That plays a role here. Now in terms of boundary conditions, the pond, right? The pond has a boundary, but we're going to assume an infinite pond. This would be like the example of maybe electromagnetic waves out in space, right? They're going to propagate infinitely far. So if we assume an infinite pond, then we don't have to worry about the boundary of the pond, but we do have to worry about the boundary in time. So the boundary in time is given once again at the beginning. So the question is, what is the beginning here? Well, the beginning is going to be the shape of the wave at the beginning. That's phi at time 0 has some shape which we determine by f. It also has an initial speed at the beginning. That means that the velocity or the derivative in time is given by g. So we need to know those two pieces of information at the beginning to get a well-defined answer here. And so that's the wave equation. There are, of course, so many more physically relevant PDEs. We're going to move onwards from there. We did kind of describe examples of how we might derive PDEs, but we're going to get into kind of the nitty-gritty details of how one might find differential equations. But we're going to do that in the next section. So for now, I hope you had a good introduction to PDEs. You saw some nice physically relevant ones, and you know what equations are, functional equations, etc. Anyway, I look forward to seeing you again in the next video. Bye.